from an application standpoint, from a performance standpoint, from a reliability standpoint, from a cost savings standpoint, from a power system optimization standpoint, from efficiency standpoint, right? Well, let's keep an eye on this power triangle. Let us assume that we have a facility, an industrial facility, automotive, heavy industry, or whatever, that is asking the utility, okay, for this much apparent power. And out of this apparent power, so let's just express this as P1 plus J times Q1, the complex power. And the magnitude is going to be P squared times Q squared. Okay. And remember that cosine theta is the ratio of P divided by S. Okay. These are the equations that basically we just have to work with. But I want us to understand it not strictly from the standpoint of the equations, but also apply it properly, right? So we are asking utility to provide us this much power, which we are going to break down into the real power and the reactive power, right? So the industry, automotive industry, heavy industry has a lot of motors, and you are actually demanding more or less the same amount of real power as you are demanding the reactive power. So what ends up happening is that your power factor is poor, right? So you almost have exclusively motor loads, right? So the utility is providing us this much. So the utility is providing P for your real power needs and capital Q for your Q1 for your reactive power needs, right? Now, this goes on for a long period of time, and the utility sends you a notice that, hey, your power factor is so poor, you were supposed to maintain at 0.90 or close to unity, but you are at about 0.70. You are about at 0.60, so you need to do something, or otherwise we are going to disconnect the connection. Okay, you get the message, and then you consult a professional engineer, consultants, and then they basically design a system where you are able to introduce a capacitor in parallel. So what this capacitor is now going to do is that it's going to provide you Q2 locally, right? Because remember, capacitors carry a negative Q sign, as we saw earlier, because of the reactance being negative. And now this motor will be able to draw Q2 from here. And instead of asking for the utility for full-blown P and Q1, which was previously the case, it is going to ask the utility Q1 minus Q2 because Q2 is being locally provided. So from the standpoint of utility, after you do, and this is called the power factor correction. After you do the power factor correction, check this out. The triangle, right? Your apparent power triangle, your power triangle in short, has a very low amount of Q2 requirement of Q requirement because you are able to actually provide a lot more react. Actually, what the capacitor was able to provide is this delta Q. Okay, should correct this. So the capacitor provided delta Q, right? And what we are now asking the utility is still P, okay? Still P, but Q2, right? So this is the new apparent power that's being provided. The P remains the same. In power factor correction always remains the same. And all we are asking the utility now is Q2. And delta Q is being provided by the capacitor locally. Now, how does this help? Well, it helps because you can see that theta 1 was larger than theta 2. Okay. And power factor, now if you want to work with the numbers, right? Cosine of theta 1, theta being large, let's say theta is 90. This is going to result in a good power factor or bad power factor. Our theta has reduced, right? So let's say theta went from 45 degrees to a theta of 10 degrees. Okay. So cosine 45 is equal to 0.5 if I'm not mistaken. And cosine of 10 is very close to 0.9 or 0.9 something, 95 or something like that. Okay. So what we have, and this is where I find people just losing track of what power factor is. Because if you just focus on the equations, you feel like all you gotta do is just punch in the numbers, right? But having this understanding that when I inserted a capacitor in parallel, then this capacitor was able to provide reactive power locally, right? And the utility now no longer has to provide this extra bit of reactive power. So the draw from the utility for the reactive power has shrunk, and the result is that the y-axis has shrunk and the angle theta has shrunk, and the shrinking of angle theta basically means an increase in cosine theta value. So my power factor has been improved because utility will no longer have to provide me the full-blown Q1. This is a whole story. This is the whole concept, the practical application of your power factor. Okay. Now, if you look at this scenario where we have a 50-50 split between the real power and the reactive power, okay, if you calculate the value of S will be equal to P square plus Q square because it's a magnitude, right? So this is going to result in 100 square plus 100 square, right, for P and Q, and that is 141, okay, for the value of kVA. And the power factor is equal to cosine theta is equal to the ratio of P divided by S. So the P is 100, but the apparent power is 141 because we also have a Q factor in here, right? So this results in 70%. So poor power factor, 0.70 power factor, okay? 0.70 power factor. And when we have a bigger share of the reactive power of the apparent power, right? Or in other words, when we shrink the reactive power, then your kVA reduces because now 100 square plus 75 square root is going to result in 125. And now when I do 100 divided by, which is still the same, 100 divided by 125, that is going to be 80%. So the power factor is improving. You're still keeping the real power the same, but you're shrinking the reactive power because maybe you have that small capacitor feeding the reactive power locally, right? And when you hit 100% real power, then your S is equal to P, right? And in that case, the ratio of P divided by S is equal to 1, and that is a unity power factor. Now, this is just looking at the power factor. There is something more interesting that is happening at the background, okay, which is the line current. The equation for a three-phase I is equal to S divided by square root 3 V, okay? So you can see that as the value of S, apparent power, is decreasing, we are going from, because voltage is held constant, right? So assuming that your three-phase motor is still going to be a three-phase motor at whatever voltage that you're working with, right? So what does that mean? It basically means that this guy stays a constant. And what we are doing is that the only variable is S. So when the value of S goes from 141 to 125, the value of I is going to proportionally decrease, right? And this is the line current. Remember, this is the line current. This is basically, if you're looking at three-phase circuit, right? And you have a load over here, this is the current that is flowing on every single line, right? So the value of I is proportionately decreasing with the decrease in the value of kVA. Does it make sense? But it doesn't stop there because the losses along the transmission line are I square R. So a decrease in current actually decreases the losses by a square. Okay. So that's the reason why the utility would prefer a customer that makes their life easy by demanding 100 kVA, because at the end of the day, the real power is really 100 kW. Okay. As compared to a customer who is asking for 100 kW and on top of that asking for 100 kVR as well. Okay, because now the amount of current that needs to flow on the lines is going to increase, and the I square R losses on the line are going to increase. And because of this larger kVA, you have to have a larger transformer, you have to have larger overcurrent protection, you have to have larger conductors, and so on and so forth. Does it make sense? Okay. So there's a question. Is it fair to say that these two things about the high motor load customer power factor varies on loading of the motor, low power factor with low loading, and it's time dependent? Number two, we can also use active power factor correction such as So the assumption is that you're looking at a facility holistically, right? You're looking at one industrial plant, and the makeup of the load is going to change. Some motors are going to be online, some motors are going to be offline, some motors are going to present a little bit different power factor, different loading conditions, and whatnot. But we are looking at the big picture view. And the fine details of how you actually manage the power factor correction, it can take so many different shapes and form. You can have, capacitors going in, going out all the time. You can, in some cases, you may also have to do load shedding. In some cases, you may actually have to respond to the conditions upstream at the utility level. Because if the utility is doing some sort of power factor correction and then they have a capacitor engaged, then your load, you can have higher voltages on your line. So the actual real-time dynamic power factor correction management, especially at utility level, higher medium voltage levels, is a very specialized field in itself, and there are multiple ways to do it. You can have synchronous condenser in the form of a motor that has overexcited field. You can have static VAR compensators and so on and so forth. So that is a whole different ball game altogether. The goal over here is to appreciate and understand what power factor is, okay, and how the math, how the formulas, how the equations translate into all of this. In the P power exam preparation, we actually use phasor diagrams to understand this even more deeply. And we basically look at how the power factor actually impacts voltage drop and voltage regulation. All right. So there's a lot more to it, but at the very least, I want you guys to walk away with a better understanding of what we're really doing over here. Make sense? And then there are formulas that can actually capture these I square R losses. This formula, if I'm not mistaken, shows up in the P power reference handbook. So if your original power factor was 0.90, you are able to improve it to unity, then you can actually reduce the line losses by up to 19 to 20%, right? Which is huge. It's a big deal for utilities, right? Or even for end users. Okay. All right. So we have a better understanding and appreciation of why we do power factor correction. What's involved here, right? And what's the whole fuss about dealing. There's a lot more to just the equations. So conceptual understanding is really, really important, because once you understand the triangle, once you understand the leading and lagging, once you understand the nature of the load, once you understand what real power is, what reactive power is, what apparent power is, it becomes a lot more easier to deal with the plug and chug equations. And if a question is twisted and curveballs are thrown at you, it will not be that difficult. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and P power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and P power exam preparation programs, please visit my website, studyforfe.com.